bit of the biology side of things. Just to show how many of us here are biologists. That means you do wet lab stuff. Get a few, that's good. So it started off when I was doing my PhD back in Australia in Kevin Nicholas' group. That was during my honours and PhD. Our lab is actually interested in milk production. How to squeeze more milk, better milk, more protein milk, whatever milk that you want from the cows. Because we are funded by the Australian dairy industry. So there was a very interesting aspect, and I was doing molecular biology, cell biology, and bioinformatics, but in the department of zoology. So it's a bit strange. And being zoologists, they like to talk about evolution. You can't escape evolution from them. So I was actually given this question: is a rat a big mouse? No, we can't answer that question. Because if a rat is a big mouse, then we can translate a lot of mouse studies to humans. Right? Because evolutionary, rat and mouse, the ancestry divide from us about 16 million years ago. Rat and mouse, 8 million years ago. So we are as different to a rat compared to a mouse. So this actually gives us a very interesting question. In biological context, we always think that a rat seems like a big mouse. We keep using it for a lot of different things. But a lot of experiments shows that it's not the case. For example, when we are studying explants, memory cells, we can put the mouse explants in the media itself. It will survive very well. We can actually play around with the hormonal concentration of the media. That works. But if we do that with a rat explant, all the cells will die. You have to float it on a paper. Nobody knows why. So this kept my interest growing, and then I went back to Singapore Poly as a lecturer. And one of the things that I had to do was doing final year projects with students. So I was thinking, what is an easy final year project? So I was thinking, maybe evolution may be something to work with. So I was given this question: am I creating some sort of monsters out there? Evolution always scares people. Just like genetic engineering always scares people in the past. But this fear is based on something. For example, killer bees are actually not natural, it's man-made. So we're creating some monsters by evolving things. Interestingly, not really. So what is natural? Okay. Before we think about what is unnatural, we have to consider what is natural. Or are most people just fearful of science? I show this picture of you should recognize some of the plants, at least 2 of the 3, right? You have broccoli, some form of rice or wheat, and carrots. But none of them are natural. None of them is natural or are natural. For example, our carrots, these are the carrots that we normally eat. And it only exists from the 17th century. Original carrots look like this, pathetic looking, short white carrots. During Christopher Columbus' time, the royal color of the Spanish family is orange. So people cultivate orange carrots as a court tribute. Otherwise, do something like that. That was from an old picture of what a watermelon looks like. I think all of you will kill anybody if you buy this kind of watermelon, right? Absolutely inedible. Bananas. I love bananas. I eat a lot of bananas. But there's always a problem. Where are all the banana seeds? We have actually cultivated them out of existence. Bananas have seeds to begin with. And you can't eat them. Currently, you have tiny little banana seeds in the center of a banana that we can eat. But with this, I think it's going to be a horrible thing to eat, actually. Corn. Corn has been cultivated for the last 5,000 years, and the interesting thing is the corn looks something as pathetic as this little guy here. It was supposed to be starchy, absolutely hard to bite. You probably lose a few teeth biting onto that. Wild corn is actually almost non-existent today. So then I keep looking. We have seen all these plants and so on, but all of them are the same species. So the first genetic engineering are those people who are growing plants. So for example, it starts off with this little kale. So we actually breed them we select them for the thicker stem, we get this gailan looking stuff. Then we breed them for more flower buds, we get broccoli, and then we breed them for less leaf, you get cauliflowers, and so on and so forth. Okay. So it's different strains of things. It's just that all breeds of dogs are the same species. But I always tell my student or tell anybody, you can't breed a golden retriever with Chihuahua. Chihuahua will die for obvious reasons. So interestingly, why we want to study evolution? To me, the most naive question and actually the toughest question are actually evolutionary questions. Where do I go from there? These kind of questions. How on earth are you going to answer them? You know that your toenail grows slower than your fingernails, but why? Yeah. Your eyebrows, eyelashes is just an inch away from the scalp. But none of you want your eyebrows to grow that long, right? Hard to trim. Okay. Wisdom teeth, why we have wisdom teeth when you pull them out? And if we have wisdom teeth, why not we have more sets of teeth instead? Okay. All of us are fearful that someday our teeth will all decay, right? But if we have 8 sets of teeth like elephants, we will not have a problem. So if we have all 4, for example, I only one wisdom tooth instead of 4, what do we do with it? And this is the most interesting question. Why is it so easy to fatten up than slim down? People who know me long enough know that I've been dealing with my weight for my whole life. And my weight fluctuates 20 kg up and down for the longest time of my life. And the reason is, I always tell people, we are descendants of those that survived Ice Age. If you cannot down-regulate your metabolism during Ice Age, you will die already. Same thing, good food are always nice. And it's actually, all the nice food are unhealthy. Right? How many of you really love salads? You just have to eat it for some reason. But if you have a diet of Ferrero Rocher, you eat them all day long, right? And carrots or whatever. Okay, so to me, evolution seems like a search algorithm by itself. You have a large search space. How do you get to the optimal sense of things? This is where the computational aspect comes in. The example that I'm giving you is, let's say you have an enzyme that you found to be quite useful. Okay. But it's in Bacillus cereus. Bacillus cereus grows at about 37, 38 degrees or so, normal human temperature. What happens if you need this enzyme to go into a bioreactor that is like 65, 70 degrees? You put it in, it degrades. Okay. It refolds itself. Basically, it becomes an egg, a cooked egg. So this is a question that was actually done in 1998 by this guy. So he was actually looking at this LUB gene, and what he did is he cloned Bacillus cereus LUB gene into Thermophilus, and he gradually adapted these Thermophilus, because Thermophilus have a wide range of temperature. He grows them at 40 degrees, slowly 55 degrees, 60 degrees, all the way until 72 degrees, 75 degrees. And he looked at what Thermophilus does to this gene. Out of about 350 amino acids, 3 amino acids has been changed. Now, that's a large space if you want to do it computationally. You can do mutation, but that's a large space to actually try out. So, but going through directed evolution, we have found this route. No, this LUB gene that has these 3 amino acids that's changed is able to function at 70 degrees. Okay, so that's important. And then I kind of look at it, okay, why not I do some evolutionary experiments? So I have 2 themes here. One is to look at E. coli, and one is to look at disuse organisms. So I'll talk a bit about E. coli first. Okay. So when we talk about evolution of E. coli, I have to give tribute to this guy called Richard Lansky. He started an experiment in 1980. started with 12 flasks of E. coli B. And every day, reculture. So now he reaches more than 70,000 generations. What happens is, the E. coli generally evolved to be able to use citrate. E. coli cannot survive on citrate naturally. So his E. coli machine evolved to use citrate now. So that's quite interesting. And I actually look at what I can do. So my very first thing that I did is, how hardy is E. coli? And this work by my students show that E. coli is actually super hardy. It survives anywhere. So what we did is, we try to get E. coli to grow in liquid culture, just a whole flask of 1 liter culture, put inside the incubator. No shaking, nothing. Every week, you just measure the viable bed count. You will see that this is log 6. That means it's still 1 million cells per mil. It dropped a lot, but it's still a fair bit. And just keep going consistent. So after 11 weeks, my students are getting irritated, because it's quite boring work, right? So we are looking at why E. coli stops. So what happens in 11 weeks? Our idea that we keep learning in school is, there is a lack of sugar, or there's always this waste buildup, acid waste buildup. Is that true? What we did is, we did a media adsorption. So after 11 weeks, we spin down the cells. We inoculate new E. coli, let it grow to half the density, spin out cells again. So we keep on using the resources from the spent media. And it took about 8 adsorptions, 8 weeks, after the 11 weeks batch culture, and the E. coli can still survive to some extent. But every week you see that the maximum growth, the maximum turbidity drops. You want to let it drop by about half. So it comes up with these 2 questions. Is there such thing as an acid base buildup? The question doesn't seem to be very likely, because if you look at the pH, it's still 7. That means after 18 weeks, actually 19 weeks of culture, the pH still maintains about 7. So what acid is there? Nothing. Then what we did is, we throw back some of the glucose, and E. coli goes back again. So that tells me that it's actually the lack of sugar, not the waste buildup, that caused E. coli not able to grow inside. We just lack of sugar. Then we also realized that we always use optical density to measure E. coli density, how much E. coli is there. But when you look at the graph, it's kind of all over the place. So we are thinking of what is the best way. We extract the DNA and found that DNA is a better measurement of E. coli. Because we actually count how many grams of DNA you can produce. So far so good. And why E. coli? First, it's a constant problem. Every year, in fact, for CDC in US, there's a page just dedicated to E. coli outbreaks in the world. Every year you see E. coli outbreaks somewhere in the world. Is that surprising, given that E. coli is so hardy? It's something that can spill on the floor. 2 weeks later, you can still culture E. coli from there. So my first study is looking at food additives, because E. coli lives in our large intestines. So it keeps coming into contact with the food that we eat and the chemicals that we eat. There's a study looking in 2009 saying that if pigs are fed with ampicillin for about 7 days, one glucose ampicillin, the E. coli becomes resistant. Imagine when you take a pill, when you take antibiotics, your large intestine, your small intestine doesn't absorb 100%. Let's say it absorbs 90%. The 10% residual is actually suboptimal. You're actually training the E. coli in the large intestine to survive, to be resistant. What does this really mean? Think about it. we never segregate our feces. We never segregate anything. Your sewage is never segregated. So what do the E. coli becomes after that? Antibiotic resistance is easy to study, but there's been extensively studied. So I'll start to look at food additives. And because in a poly context of grants, which is marginal, food additives is also cheaper. And the three food additives I look at is our favorite MSG, table salt, and benzoic acid. Now, MSG and table salt literally I just buy from the market. Just market supply. Benzoic acid, I get it from one of my colleagues, which is doing on food preservation. So then I culture them into two high-load concentrations and so on. And I keep passaging them. So my students actually continue up to 140 passage. I break up the study into first 70 and the next 70 passage. No real reason, simply because the first 70 passage is one batch of students, and the next 70 passage is another batch of students. There's really no reason for that. So these are the kind of treatments. So we look at the high and low concentrations. And then maybe we do a few things, because as diploma students, they are just very good at culturing things. If you ask them to do too much experiments, they'll just mess up for you. So keep culturing. Every Monday, Wednesday, Friday, come back and culture. Every Friday, you do the cell growth measurements and so on. So it's an easy piece of work. But they're quite diligent with doing that, to the extent that within 1 year, they produce more than 4,000 OD readings. Now, how do I know that E. coli has adapted to the media? Basically, the generation time keeps increasing. Okay, so the generation time decreases. So when under stress, you take longer to divide. When the generation time you grow faster, means that you're adapting. So we can see that the first 70 passage, everything seems to be adapting pretty well. After which, what we do is we do DNA fingerprints to actually try to see is there any contaminations, and whether is this adaptation a genetic adaptation or biochemical adaptation. And we show that there's actually a genetic adaptation by looking at the differences in the DNA profiles. It's just DNA fingerprints because there's no money to do next generation sequencing. It doesn't really exist in 2007. Okay, but after 70 passage, you look at then the next one. You see that the cells seems to be more or less stagnant. There is some increase in generation time now. So it means that after the first initial adaptation, the cells are actually just growing randomly. And you can see that the genetic variation actually just fluctuates all over the place. So after 2 years, I decided to stop this experiment because anything more is kind of not much fun already. I can see that there's a big steep from the first 70 passage, and then after that it can't remain static. Then on the second year, I decided, okay, if E. coli can survive so well, why not stress it and see how well it can be stressed? And I call this halophilizing E. coli, basically get E. coli to survive in more and more salt. You know, every now and then we have beaches that is being contaminated with E. coli because of all the sewage. In fact, Singapore just had a case a couple of years ago. I can't remember exactly where though. E. coli contamination. And from our first study, we are quite confident that E. coli can adapt. Now, usually on textbook, E. coli is a non-halophilic bacterium, which means that it cannot survive, the salt density can survive about 3% at best. So the Staph aureus on the skin survive up to 5% or more, 7%. What I did is, I get the high salt, which is 1% on top of the media itself, as a starting point, I keep adapting it more and more. Basically keep squeezing it. Now this adaptation plan is not pre-planned because I will see how well the E. coli grow in the MIC experiments and so on. But you realize that we did a span of 80 passage, so you divide by 3, that's about half a year's time. We are able to get it to grow up to 8%. 8% is very high salt concentration. Your normal seawater is about 3 to 4% salt. And what we did for the minimum inhibitory concentration is we try to look at, we try to grow up to 11%, we test up to 11%. Because you grow up to 8% salt, you have to test up to 11% or something more. Why don't we go more, 13%, 15%? It's just quite hard to do. The saturation point for salt in water is 21%. So actually at 11, 13%, it starts to precipitate our solution quite easily. So that's maximum input. But you realize that at 60 passage, when it's still in 6% salt media, you see a spike from 60 passage onwards. It means at this point in time, the E. coli is behaving as though it's a salty bacterium. And you realize that it can still survive in the earlier parts of it. It doesn't shift. So you have a big density growing at this end here. The worst case scenario is contaminated. And the easiest way to contaminate your E. coli culture is the Staph aureus on the skin. Okay, because it's salt tolerant. So what we did is, we did just a gram stain. Easy, because E. coli is gram negative, Staph aureus is gram positive, so it will show up immediately. If there's a contamination, you'll see it. Okay, you'll see the blue dots. And we did, for different passages, a DNA fingerprint. If the DNA fingerprint just go messed up, that means you have two different cultures at the same time. But as I say, at this moment, it doesn't seem to be messed up. So we are quite sure that it's still E. coli. And the third step to be sure that it's E. coli at every glycerol stop. Before we store the culture, we actually plate it on McConkey agar first, okay, to kill off all the Staph aureus. What does this really mean then? First, E. coli is very hardy. No surprise, it has to be hardy. Think about what rubbish is in your large intestine for. It's in everything. The most important thing that I kind of realized is the adaptation rate could be pretty serious. What does this mean? I always ask is, if you have an E. coli contamination in a food processing plant, your salami is not going to be 11% salt. After half a year, 4 months, your food processing plant will be in trouble. Right? If you let E. coli continue to grow inside a food processing plant, how much salt can you provide your food? And for public health, what happens to antibiotic resistance? This is whereby I go to the next part of looking at digital organisms. Because antibiotic resistance is quite tricky to study. First, antibiotic is expensive. Second, I've left SP then, so I don't have a lab anymore. We always find this thing called superbacteria, and we have superbacteria that's resistant to everything all over the world. And yeah, this guy is one of my cute little bacteria, Treponema pallidum, which is for syphilis. So it is resistant to a lot of antibiotics these days. In the past, you can still treat it with penicillin 5. Now a lot of penicillin cannot be used, so it's going to be a trouble. So what is the difference? There's actually no difference in the sense that antibiotics to a cell is still a chemical stress. To a cell, you either evolve or you die. No difference from it. And we go back to the study of the ampicillin as well, shown that E. coli can grow. So what happens at this moment is, if antibiotics is a stress, and we know that there is a lot of antibiotic resistance, what happens if we remove the antibiotic stress? The question is, will we be able to reverse the tolerance? So think about a situation whereby If we know that ampicillin is quite useless, in fact, when I was a child, most doctors give me ampicillin. Now no doctors give me ampicillin. It's amoxicillin now. Okay. Even amoxicillin is quite useless. You have to use amoxicillin plus carbonic acid. So the question is, can we actually stop ampicillin use? And after maybe X number of years, all the bacteria somehow become ampicillin susceptible again. Can we reuse antibiotics after certain years? That would be quite useful, right? Just stop for maybe 10 years and keep reusing it. At this point, you realize that pharmaceuticals are not producing more antibiotics because it's cost ineffective. So the idea is, if there is antibiotic use and there's a resistance, no matter what, after we discontinue, is it possible for the resistance rate to drop so that it can reuse, or will it become static? That means locked in the population. So there are two camps of study. One says that yes, discontinuation eventually leads to reduced tolerance. They look at that in insecticides in 1950s. And in 2005, it also shown that some antibiotic resistance, or the prevalence of antibiotic resistance, actually drops after several years of disuse. On the other hand, we have another camp that says no, it maintains. So it is shown in also several studies. So the reason why I put this in 2005, you realize that it's actually in between. In fact, 2005, 2010, 2009, 2001. So you have both camps saying different things at the same time. Which one is true? The problem is, can we run such experiment in the lab? You can try. Can we actually produce some antibiotic resistance in people and see what happens after that? Well, it will be hard to get any ethics approval, right? So in that case, we can use digital organisms to simulate what we know about evolutionary process. So what happens is we use that to test some hypothesis. Now we go back and look at some of the used successful case. So looking at evolution of genomic size, how genome size actually adapts itself. What is a suitable genome size for bacteria? Looking at protein complexes and so on, or changing environments. So at this moment, I decide, okay, why not? I'm doing a lot of programming. Why not develop a software called DOSE, which is actually just a library, a Python library, to simulate my organisms. So I was working with Clarence, who is sitting here. The idea of DOSE is quite simple. First, we set up a three-dimensional world. It is X, Y, Z coordinates. So every world is a cell. Or rather, it's cells in a world. Think about it like a Rubik's Cube. Then you create a set of digital organisms, which is in a computer. So first you start off with the same clones. You can have different clones as well, that's fine. After which you scatter into the world. Kind of throw them, scatter around into the world. You define a fitness calculation, how you want to train the cells, a population, mating scheme, propagation scheme, and so on. Then you run. Now, being a biologist myself, most digital organisms, they have only one means of control, which is what is the fitness? Are you supposed to grow to the next generation? But for me, I try to come up with different ways. I want to have different ways of controlling. Okay? For example, I want to have this thing called pre-mating population control. Okay? For reasons such as, can I actually simulate childhood removal? People die before they get into sexual maturity. What kind of mutation schemes do I want? After which I can have post-population control. Okay. You can actually generate different cells to die. You can also put in generational events. For example, what I always say is, you simulate a volcanic explosion every 100 generations. Okay. It's not something ad hoc, or rather it's something ad hoc. And because you have different cells, you can actually move the organism around the different cells. So we test it on a simple case. We have a flat world. Think about it as a 5 by 5 So it treat it as though it is a 5 by 5 village, 25 village population. We end up with 50 organisms per cell. So the genome is actually just 5,000 bases, small genome. Mutation rate and so on. What I'm trying to look at is, at different mutation rates and different migration schemes, so the organisms can only mate within the cell. So it can only mate within the village. If there's no migration, it means that these 25 villages are actually isolated. Pretty much like what happens in Dark Ages in Europe. People are just isolated in different communities. Adjacent migration means that the cells can move to adjacent sites. Okay. That is pretty much like our roaming behavior. You just go to one village and then settle down for one generation, then your kids go to another village and so on. But these days, what we have is this thing called long migration. You fly across the world to mate, which is quite common. How does this affect the genetic variability? When we look at the genetic variability in the village itself, what do we see is, if there's no migration, you are very isolated. So within each village itself, the variability drops. It's actually pretty low. Actually, it doesn't drop, it's just low. But when you actually allow the cells to move, because you have some inputs and outputs and so on, the variability actually increases. The problem is, when you have long migration, the whole world now becomes almost like a big cell. What does this really then mean is, we know that genetic variability is important for our disease tolerance. If we are clones of each other, we died a long time ago as well. So that everyone has some form of adaptation to diseases and so on. What does this mean then? If our world is actually becoming like a giant village, the whole world's variability actually seems to have dropped. That could be a possible outcome. So then the argument is, migration is actually important, but long migration is actually detrimental. And that's been shown by a couple of studies as well. So overall, we are becoming a global village, as I mentioned before. Yes. And disease resistance could be a problem. That's what everything is leading up to. It's also quite interesting. When I was in Australia, there was once I fall pretty sick. I went to a hospital, and the infectious disease registrar had no idea what happened to me. The month before I was in Singapore, and the month before I was in Taiwan. So now she goes into a big panic mode. She has to test for everything that's possible, which is quite scary actually after a while. So I was a bit anemic. On one hand, she gave me a liter of blood. On the other hand, she draws out another liter of blood. I will assure you that it's not very comforting if infectious disease registrar comes in with 2 bags of tubes. Okay. You're just looking in and out. That's what she did. But then you'll see something quite interesting. Is that there was the same night I was lying in hospital bed, and the nurse was taking my blood pressure and said that your blood pressure looks pretty low. I look up at the nurse. This is 3 a.m. in the morning. How stressed you want me to be? Yeah. And because of that, my blood pressure being low, she pumped 1 whole liter of saline into me and caused me to go toilet. Please, I need to sleep. Okay, then we look at the second part, which is antibiotic resistance. So what happens if we go to a case whereby there's no genetic cause or there's no metabolic cause of maintaining resistance? So first I start off with just one cell, 100 digital organisms, and a genome that is just 1,000 binary bases, so it's 1010 times 500 of it. And I set up 1% mutation. Second phase is I stop the selection. So see whether does the genetics actually drops to baseline. Then I keep going back. What happens if I take that and then I repeat the gain of resistance again? How rapid will it grow up? I keep repeating this phase 3 and 4. So the resistance is essentially I define it as blocks of zeros, 2 or more zeros. So you have 1,000 ones and zeros. So for example, if you have 2 consecutive zeros, it's resistance of 2. But if only 1 0, then there's no score. So the higher score, the better it is. And I define my maximum block that I can go is 11 zeros. And I need 10 to gain maximum resistance. I need 10 blocks of 11 zeros, which is actually not easy. So again, this is what happened. Originally, we did this thing called a truncated, which means that top 10% of the fittest organisms goes to the next generation. Then we submit the paper, and the reviewer came back to us and said that is suitable, but not. It's too stringent. Okay. Why not we do this thing called fitness proportionate selection? So the probability of mating for next generation depends on the fitness scores. Nevertheless, this is what we see. At 200 generations, we did 25 replicates of it, so this is an average of 25 replicates. The higher the resistance, the higher the fitness. You see that no matter how many, my 11 is actually the toughest, it hits the maximum resistance. So the cells actually adapts pretty well. It gets tolerant. Then what we did is, what happened when you remove it? So it's randomized process, absolutely random now. You find that there's a massive drop in the resistance trait, but it doesn't drop to 0 because this is the control baseline. So which means that there is, when you remove the antibiotics from the system or from the world itself, there may be a drop in the resistant trait, but it doesn't go back to pre-antibiotics era. Because it's higher than baseline resistance, it really has an implication on what is the suitable therapeutic dose. For example, if this, that means you have to take a higher dose of antibiotics for it to work. Right? So instead of 400 milligrams of ampicillin, you may have to take 800 grams of milligrams of ampicillin. A lot of people can handle that. What is more interesting is there's a big plateau. After you drop, there's a plateau. And remember, I start off adapting it to grow in the antibiotics for 200 generations. I de-adapt it for 5,000 generations. The proportion is very great. So I want to know what happens in this portion here. Is it a flat line or is it not a flat line? When I do a linear regression, it is statistically not significant from 0 because the slope crosses 0. What it really means is, remember the two cases, one can say that it will drop, one can say it doesn't drop. It's actually a genetic, it's actually a statistical variation. Depends on which side you're on. And because the drop is so low, at the very least, it will take 175 generations in this case, 175,000 generations to adapt to this line again, compared to just 200 generations of getting up. So we can see there are situations whereby it will never lose resistance. So then we go to the next part. What happens when we try to stress the cells again? This is the initial, the second round, it goes up fast, even faster. That means, let's say ampicillin, after 10 years of disuse, you think that most cells have adapted to, have lost some of the resistance. The moment you use it, it will just be a few months before you get all the resistance back again. So what's going to happen? So this is for every case that we have. So you keep repeating it multiple times and it just keep varying on itself. Which means that it's actually quite useless to do that. So we are thinking, okay, maybe if we do not have a metabolic cause, it is not a suitable way of doing things. Maybe we put in a metabolic cause. So the easiest metabolic cause that I can think of is a GC content. Because I'm using ones and zeros, right? I just count how many ones versus how many zeros. That is my GC content. The idea is this. If bacteria is, or if any organism deviates from its own GC content, it doesn't grow very well. So GC may be a trade-off, maybe like a limiting factor. However, when we do it, there's actually no difference at all. So at the very least, it says that putting in simulating a cost in maintaining resistance doesn't seem to work. We may need more cost on that. So in this work, what I've shown is genetic resistance in field studies. First, is contradictory. There's no way of showing which one is a correct model, experimentally or otherwise. So digital organisms provide a useful experimental tool that we can use. But in the antibiotic resistance cases, the drop after disuse of antibiotics is actually quite weak. So which means that trying to reuse antibiotics is actually quite hopeless. That's not very appetizing for most of us, right? Nothing very much we can do. So we'll stop there, and now I will go through a little bit of what is the real limitations of digital organism simulation. Ideally, we can simulate everything. Sadly, it's not possible. Now, there's actually this idea that genetic variation is actually mutation, caused by mutation. And the way mutation is retained, or the variability, is by natural selection. But the question is mutation technically equals to biological evolution? Richard Watson actually asked this question in one of his papers. The way he phrased it is actually almost like an